Okay, welcome back. So we're into kind of our last topic here. We'll have a couple of days on dealing with planes. So first thing, I guess, what is a plane? I don't want to use that term and then have people not recognize what they should be visualizing. So it's a flat, infinitely large, two-dimensional surface. If you think about the fact that a line continues out forever in whichever directions it goes, uh, the plane is the flat surface that does the same thing. So when we've worked with lines in the past or graphing in the past, the XY plane is an example of a plane. So how do we visualize this? Well, the piece of paper you're working on, the computer screen you're looking at, the blackboard your teacher might have written on, those are all planes, if you can consider the fact that they could continue out infinitely in all directions. And so a couple little examples here, I just pulled off pictures off the internet. So the first one is your, sorry, trying to cite these here, is your XY plane. So we can't draw it infinitely large, obviously, but the idea is that it's that perfectly flat surface that goes through X and through Y, and that is perpendicular in this case to Z. Other examples, sort of the XY plane, the YZ or XY plane, the YZ plane, sort of each one, of course, could continue out in each direction, and each is perpendicular to the other axes in each case. And then this one down here shows three planes. Again, not that easy to visualize, but if you pick up three pieces of paper and hold them one over top of the others, you can see it pretty clearly. This plane could be parallel to this plane, so just over top of it, going the exact same direction. Same sort of thing here. Planes obviously could intersect. We'll get to that a little bit later. So how do we represent a plane? How do we write an equation for one? Well, we think about starting it with a line, and a vector equation of a line gives us a point and then the direction that that line goes. The plane now will go out in kind of a flat area. It'll go out in the same direction and then off to the side as well. So basically, what are we missing? We're missing a second direction. So as an example here, this equation looks a lot like the previous one, but it would represent a plane that contains that line. So this is the line, and then the line can also go out in some other direction and form a plane. And as I said, this is just an example. The reason I picked 2, -4, 5 was because I wanted to pick 2, -4, 5, not because it's the right answer. Again, if you can sort of picture a line in space, you could draw a plane in any of the directions. So hold a pencil up and then put a piece of paper beside it, or put a piece of paper on top of it, or put a piece of paper half lying on it, underneath it. Those are all planes that would kind of contain that line and would go out in different directions. So again, just an example. And then as we had before, we have a vector equation for our plane. We will have parametric equations for the plane. In this case, the x value is established by taking the 3 from the point, adding the -1 times the scalar value in the one direction, and the t scalar value times the 2 in another direction. And that's how you can establish an x value and so on. So our second option is that we have A, B, and C representing the direction of our vector. Now, the question is, how can that be? If we required 2 direction vectors up here, how is it we could actually rewrite this thing with only one? Well, it kind of goes back to this. If we think about the XY plane here, we have the X direction, we have the Y direction, of course, or we have the 2 directions that are perpendicular to Z. We have the 2 axes that are perpendicular to Z. A little harder to see maybe in these other cases, but the same sort of thing. The YZ plane is the plane that contains the Y's and the Y and Z. It's formed through Y and Z. It happens to also be perpendicular to X. And so the only way to really use a single vector is to use the vector that is perpendicular to both of the original 2. And so I'm saying hint, it doesn't really become a hint anymore because I already told you the answer. That is the equation, that is the scalar equation that matches up with this vector equation. And basically, if we to get a vector that is perpendicular to both of the original two direction vectors, we have to take the cross product, also called the normal. Normal just means perpendicular to. And just so you know, the value 20 is obtained by plugging in your point for x, y, z. Okay, so this is the vector now, 39, 17, negative 2, that is perpendicular to the plane that we were talking about. And then using the point that we had in the other equation, plugging it into those three spots, we can find the 20. And so basically that's what this next page is. Just kind of the solution here to going through rewriting that plane in scalar form. So we recognize this is our vector equation, or sorry, this is one direction vector. This is the other direction vector. Whoa, I forgot it did that. This is the form, so we're trying to find the A, B, and C, which is the perpendicular, the vector to both of those. And so I've just kind of gone through the solution here. I don't have to read it off to you. Take the cross product of those, work it out. And then, as we said, X, Y, and Z represent a point on the plane. So we plug these values in that were the point vector, the point from the end of the point vector in the original equation. And solving that, we get the value 20. Therefore, that is our vector equation. Sorry, that is our scalar equation from the given vector equation. Second example here is a little different. I don't have a solution, so we'll go through it. I haven't stated the solution, I mean, so we'll go through it. Sorry. So we're looking to find the intersection of a line and a plane. Now again, we should be able to look at this, or not again, but at this point we should be able to look at this and recognize, because there's only one direction vector here, this is a line. The scalar equation is written this way to represent a plane. We don't have a scalar form. We don't have a scalar form that looks quite like this anyways to represent a line. And so the different possibilities are a line could be parallel to a plane, either above it or below it, and have no point of intersection or no intersection at all. A line could pass through a plane, as you can see here, and of course there'd be a point of intersection, or the line could be contained in the plane, so actually part of the plane, and the plane could spread out across the line, in which case there would be infinitely many solutions. Whenever we're looking to find the intersection, we're basically asking, where do they hit? Well, here they hit at infinitely many points, here they hit at one point, and here they simply don't hit. Now again, the solution here is actually relatively simple. You wouldn't necessarily get there on your own because you don't, sort of think that you know how to do it, but the math is going to be fairly easy. It stems from the fact that what we're asking you to try to find is the point. Is there a point there? If it turns out there are infinitely many points, that's fine, we'll figure that out. If it turns out there are no points, that's fine too, we'll figure it out. But what we're looking to determine is, what is the x, y, z here that is also a same x, y, z combination on that plane? And so we'll start the same way we did with intersection of lines. We're going to rewrite, this is sort of step one, if you will. Rewrite our lines in parametric form so that we can isolate the x, y, and the z. We now have little equations for x, y, and z. Those values can be substituted into the plane. X is exactly this. What this means is, don't forget, this is saying x is exactly the same as 1 plus 4t. Y is exactly the same as 6 minus 8t. And z is exactly the same as 8 plus t for every single point on this line. So if one of those points happens to appear over here as well, we can use these little expressions to represent the x, y, and the z. So substitute those in for x, y, and z. Of course, now we have one big equation with only one unknown value, and we can simplify it. and we get down to 38, negative 38 divided by 56, which is the same as negative 19/28. Once we've got that figured out, let's just hide this for a second. Once you've got that figured out, of course, what we want is the actual x, y, and z values. We don't just want the t value. And so the third step now is substitute the t value back in to determine what x, y, and z actually represent, actually equal. And so if I go to solve this, I can simplify a little bit here. And so I have negative 19/7 and 1, which is 7/7, plus negative 19/7 or minus 19/7 will be negative 12/7 for x. If I try to solve these, simplify again a little bit, that's a 7, that's 2. So divide both by 4, and now I'm going to have 42/7, and negative 2 times negative 19 is plus 38/7, which is 80/7, and this one is simply, it's got to write in 28ths, I guess. What's that? 4, 6, 16, 22. You don't have to tell me if this is wrong. I'm not really too concerned. And so, assuming the math was right there, I'm going to have 205 208ths, which means that, therefore, our point of intersection is negative 12/7, 80/7, and 205/28ths. So again, may have made a mistake there, but mathematically just that's how we're solving. Determine what the value of y is, determine what the value of x is by subbing the t back in. Sub t into the parametrics. Now, just sort of a quick comment at the end here. A little bit pushed down. The other two possibilities are, if I try to solve this, I'll go through the exact same process, and I'll get to the point where I don't get a nice number here. Now, you might argue that negative 19/28 is not a nice number. Of course, it has to be a nice number because it's a really real number, and all numbers are nice. Different possibilities then. If I have a parallel, if I have a situation where the line is parallel to the plane, I'll get something like this. Not necessarily those exact values, of course. It doesn't have to be a 4, but something that has no solution. If you try to solve this, in theory, what you're going to write next is t is equal to 4 divided by 0, which clearly we can't do. So there's no solution to that. That means that there is no intersection. And of course, that makes perfect sense. I'm asking you to find the point where this line hits that plane. It doesn't happen, so you come up with nothing. No possible answer to come up with. The second possibility, of course, is if the line is actually part of the plane, there's going to be infinitely many solutions. And so we get something that looks more like this one. And what this says is t can be any number that when multiplied by 0 gets me an answer of 0. And of course, what that means is t can be any number. And so if we can sort of reason through that, we realize every single value of t you could possibly make up will get me another point of intersection, which means that there's an infinite number of points of intersection, and the line is part of the plane. So that's basically it. The final comment, of course, is if you saw the same question, but it said find the intersection between the line and the form and the plane, sorry, and the plane is in vector form. Do the two questions together. Rewrite it first into scalar form and then solve it this way.